So once you're familiar and comfortable with this formula for the magnetic force on a charge moving through a magnetic field, we should consider some of the extensions to this. For example, as soon as you start talking about a force, we could certainly relate that force to Newton's second law. And so because of that force, this object moving through a magnetic field will feel an acceleration. And that acceleration will be equal to the force divided by the mass of the object. The other thing that we should remember is this force causes circular motion. So once we know this force, we can relate it to the centripetal force on the object. As an electron or proton moves through a magnetic field, it feels a force that is always towards the center, and therefore the centripetal force is this magnetic force on the object. So we're going to see some progressions from this magnetic force. Oh, and by the way, this acceleration is, let me just clean it up a little bit here. This acceleration is not just any acceleration, it is the centripetal acceleration. So this is AC as well. So you'll see questions where the description or they describe a charged particle moving through a magnetic field. As it enters the magnetic field, it travels in the path of a circle. And so we can start to talk about things like what kind of radius of circle it is. If I sketch that out up here, for example, here's a charged particle, let's say it's an electron or something like that, moving in some direction this way, give it a velocity in that direction, and it enters into a region here with a magnetic field. As it enters that region, it will curve in some sort of circular path. Maybe just part of a circle, it could be a whole circle or something like that, but it'll come in here. Let's make these out of the page. So as this charged particle moves through this magnetic field, so number one, we could predict which way the force is on it as it enters, so we can predict which way the magnetic field is. If this is a negative object, then it'll enter this magnetic field and should curve in the upward direction, so it might curve in this circular path this way. So we can start to predict the radius of the circle that this thing is tracing. It's tracing a huge circle here, or a larger circle. I haven't shown the whole thing, but you can see how it'll travel in the path of this circle. So this is the most common extension of the formula for the magnetic force in a magnetic field. Let's take a look at an example question. So if we look at this question, to give you the scenario below here, we have an alpha particle, if it's not clear, moving at a given speed and enters a magnetic field. And the question is, what is the radius of the path of the alpha particle? So as this alpha particle enters this region, we have a magnetic field that is into the page based on these vectors going into the page. So as this alpha particle enters this region, it will feel a force in, check with your right hand, but I believe it'll be in the upward direction. And the question is, what is the radius, if I consider this a part of a circle, what is the radius of that circle? All right, so we have a little bit of room to work here. Let's take a look. I guess the first question is, let's find out what is the force acting on the alpha particle. So the magnetic force should be equal to Q times V times V. Got the perpendicular symbol in here, and we're going to be strict about it. We have the absolute value symbols around this force. So let's put in all the information we have. We have the charged particle, 1.6, no, alpha particle, so it is 3.2 times 10 to the minus 19 coulombs, multiplied by the speed of the alpha particle, 1.65 times 10 to the 6 meters per second, multiplied by the magnetic field strength, which is 5.2 times 10 to the minus 2. 5.2 times 10 to the minus 2 Tesla. So take your calculator out and prove to yourself. I get an answer of Just have to round it to two significance digits. It's 2.7 times 10 to the minus 14 newtons. So that's the first step in this question. That's the magnetic force acting on this thing. Then we have to consider that that magnetic force causes this centripetal motion. As it enters this magnetic field, the force is always perpendicular, so it always equals the centripetal force, and the formula we'll use now is that centripetal force is mv squared over r. And we have all the information we need. It's an alpha particle. We can look up its mass. It's 6.67 times 10 to the minus 27 kilograms. Multiply that by the speed of the alpha particle, 1.65 times 10 to the 6, 1.65 times 10 to the 6 meters per second, and then divide all of that by the radius, which we just calculated to be 2.7 times 10 to the minus 14 newtons. So putting it all together, oh, wait a second. Mass of the alpha particle. Sorry, got this one wrong. 6.65 times 10 to the minus 27. Okay, good. Now I'll put this in my calculator. Let's see what we get. And don't forget, this is squared, so you get an answer. So mv squared over r. Final answer of 0.68 meters. So it ends up going in a circle of about 68 centimeters in radius. Okay, so we'll leave that there. That's an example of a question that we could extend from simple application of the magnetic force on a charge moving through a magnetic field, and then extend it to our prior knowledge about circular motion to solve for, in this case, the radius of the circle that the charged particle travels in. Again, this is a common question. It's not the only question. We'll see other examples where we have to draw from our prior knowledge in order to understand, or in order to apply and use the magnetic force formula, but this is a good starting point.